We're accustomed to a very specific relationship with artificial intelligence. You type a question into a chat box, and the system types an answer back. It operates as a closed loop, isolated from the outside world. Safety testing usually reflects this setup by focusing on screening the user's text prompts. When models pass these isolated single-turn evaluations, AI developers report high safety scores as proof the system is secure. But modern models are rarely deployed as isolated chatbots. They operate as autonomous agents, wired into external tools, live databases, and code environments. The Failure First project tested these systems at scale, evaluating 120 models with over 18,000 prompts, designed to probe these structures. This research was designed to see if the safety methods used for isolated chat windows still hold up when the model is plugged into a wider software ecosystem. The first architectural layer to consider is the input. In an agentic system, the model ingests instructions from multiple sources simultaneously, and the user's prompt is only one part of that stream. When an AI agent connects to a new plugin, it reads a skill file to understand how that tool works. Attackers can use supply chain injection entirely. Across 6 different small open-weight models, hiding instructions inside these skill files achieved an attack success rate between 90 and 100%. This happens because standard safety training focuses on the user input channel. The AI treats information arriving through the tool loading channel as a legitimate instruction, allowing the payload to reach the model's core unobstructed. In an agentic pipeline, any external plugin or skill definition becomes a potential vector for a hostile takeover. The second architectural layer is the output. While a typical chatbot responds in conversational text, an agentic model often communicates with other software using structured data formats like JSON or YAML. Attackers exploit this using format lock attacks. They instruct the AI to generate harmful content, but demand it be structured strictly within JSON code. This reveals what researchers call the faithfulness gap. The models focus so heavily on the complex task of formatting the code correctly that they fail to filter the actual text they are slotting into the data fields. This technique is effective even against frontier models. Claude Sonnet 4.5 showed a 30% failure rate. Gemini 3 Flash was at 24%, and Codex GPT 5.2 reached 42%. Relying on conversational text for safety evaluations means missing the dangerous payloads embedded inside structured code. The third layer is memory. A common assumption in the industry suggests that more capable reasoning models are inherently more resilient to manipulation than simpler ones. To test this, researchers used crescendo attacks, a method that exploits an AI's memory by slowly escalating the severity of requests across a long, multi-turn conversation. The data shows a sharp contrast. Small models often forget the earlier context and fail the attack at a 10% rate. However, against a reasoning model like DeepSeek R1, the success rate climbs to between 80 and 90% as the conversation length grows. A reasoning model's ability to perfectly track context is exactly what an attacker weaponizes. Because the model remains committed to the logic of the previous turn, it is more likely to be led toward a harmful conclusion. For an AI agent, a larger context window also means an expanded attack surface. These vulnerabilities suggest a logical question. Why haven't these issues appeared in standard safety benchmarks? The problem lies in how safety tests are graded. Most automated benchmarks use keyword-based classification, scanning the AI's response for specific trigger words to decide if an attack worked. The Failure First study found that these keyword heuristics inflate the reported risk of simple attacks by roughly 2.3 times. Keyword graders have an 88% false positive rate, often labeling a response as a successful attack even when the model refused. Correcting these errors with LLM grading caused the aggregate attack success rate to drop from 36.2% to 15.9%. This creates a blind spot. Benchmarks over-report the risk of conversational text attacks, while failing to detect the real threats hidden in JSON formats and external tool files. The Failure First dataset shows that securing a modern model requires moving past the single text prompt and testing the full interconnected architecture.